On behalf of BIC Magazine and our sponsor, Montrose Environmental Group, I'd like to welcome everyone to today's presentation on latest advancements in air measurement technologies. Hi, this is Robin Dupree from BIC Magazine. I have a few pointers that I need to discuss in regards to your webinar console. You can maximize or reduce the size of any of the windows. At the bottom are widgets to access resources. And there's a Q&A box on your screen to text in questions anytime during the presentation. The Q&A portion will occur at the end of the presentation. Please join us in live tweeting during the course of this presentation and share your thoughts with our Twitter audience. Please use the hashtag BICWebinars. And if you experience any technical problems, click the yellow question mark to go to the Help Guide page. And now I'd like to thank our sponsor, Montrose Environmental Group. Montrose Environmental is an environmental services company with more than 60 locations and 1,300 employees. As one of the largest companies focused on environmental solutions, they support government and commercial organizations with a diverse range of services. Montrose expertise covers everything from comprehensive air measurement and laboratory services to regulatory compliance, permitting, engineering, and remediation. Go to montrose-env.com for more information. And now it's my pleasure to introduce you to today's presenters. Our first speaker is Peter Zemek, Senior Vice President for Montrose Environmental. He leads the Emerging Technologies team and has worked in the environmental field for over 30 years. He holds a patent and patent applications on laser technologies and sits on the Department of Commerce Trade Liberalization Subcommittee and other boards of trade lobby groups. The second speaker is Dan Fitzgerald, Vice President at Montrose. He directs the Target Emission Services Division that provides alternative LDAR service solutions across North America. He leads initiatives that support the oil and gas, petrochemical, and chemical marketplaces. He has 41 years' experience as a leader in stack emissions and ambient air measurement services. And now it's my pleasure to hand the mic over to Peter.
Yes, thank you. And thank you for attending our webinar today. I just want to point out I do have a little bit of a cold, so if you do hear me pause for a minute, I'm on mute coughing or sneezing. So just glad I'm not there in person with you. So, all right, I'd like to talk about today some of the new technologies that are emerging in the environmental field. And we're using these technologies on everything from source testing for both organic and inorganic compounds, as well as ambient testing, remediation, biogas, and other types of processes for either process optimization, for emissions compliance, for low-level ambient monitoring, for difficult-to-measure compounds, as well as other applications that we'd love to talk to you about. So some of the emerging technologies that we're going to discuss today is on this list in front of you. One is called the optically enhanced FTIR. So this is an FTIR that is now a disruptive FTIR, which takes a system that can measure many different types of compounds down to a system that can measure only a few compounds, but at extremely low levels into the single-digit part per billion level. Next technology we're going to talk about is what's called a gas chromatograph coupled FTIR. And FTIR actually stands for Fourier Transform Infrared Spectroscopy, or spectrometry, as some people would like to use. And the TDT itself is really a thermal desorption tube. So what we're doing is capturing compounds on the thermal desorption tube, running them through a GC for separation, and as they exit the GC column, we're using the FTIR as the detector, but we're doing it in such a way that we're eliminating interferences to obtain extremely low levels. The next technology is a proton transfer time-of-flight mass spectrometer on a mobile platform, and we'll talk about this in detail. It is an extremely sensitive device that can now be taken out of the brick and mortar laboratory and taken into the field, and is rugged enough now to be used on a mobile platform for real-time measurements down into the, in fact, part per trillion levels. And I'll show you some case studies that we've done with this device. We'll also talk about some laser-based FTIRs that we're assisting in developing. for now treating facilities as essentially a circus tent, or some people might say bubble. And that is in fact where a lot of the environmental regulatory authorities really would like to move, and that does include EPA. The next technology I'd like to talk about is a quantum cascade laser photoacoustic system. Now, this system, because quantum cascade lasers is still a maturing field, quantum cascade lasers actually lays in the mid-IR, which is an advantage over tunable diode lasers because they lays in the near IR. And in the mid-IR, you actually have increased sensitivity, even though you have more interference. So we'll talk about that, but this is primarily we're developing for a benzene-specific type of low-cost or mid-cost sensor. We'll also talk about some of those sensors, the low-cost sensors, and some of the Montrose triangulation platforms that have been developed to both handle the large amounts of data that are coming in and also be able to perform what you might say information that can be used to address problems in real time. So in other words, we can provide leak detection in a very quick time period. So if there's a problem on the facility, or whether it's on the facility or entering the facility, this platform can very quickly determine where it's coming from. We'll talk a little bit about drones and sensors. Drones, obviously, everybody has seen many different articles. You're probably bombarded with marketing information on drones and what they're doing nowadays. And now that the federal authorities have actually softened their view on line of sight for drones, the drones are actually spreading very quickly. And sensor technologies are also improving so that we'll be able to use these sensors on drones, and I'll show you some case studies that look very promising. And then my colleague Dan Fitzgerald will be talking about the CEMS particulate measurements, which is very advantageous to a facility for measuring particulates, especially 2.5 micron, primarily because every time we do this, we generally can see at least a 10-fold reduction in the concentration reported for the particulates. And that's primarily because of the problems with the EPA Method 5202 trims. But I'll let my colleague address that. All right, so the first technology we're going to talk about is the Starboost technology. So this is the optically enhanced FTIR. And so what this involves is essentially taking an MKS incorporated Fourier transform infrared spectrometer, and then it gets sent to another company, and that company, in fact, optically enhances it, which means what they do is they take optical filters, otherwise known in the field as cold filters, and what they do is they install this in front of the detector, and by doing so, you are reducing the photons of non-interest. You're eliminating them from reaching the detector. This has the effect of improving the signal to noise on the system in the region of interest, where the 2 or 3 compounds that you're looking for come out. And we've actually done this with formaldehyde and ethylene oxide, which we can easily reach single-digit part per billion levels. And this has been field tested and validated with EPA Method 320 and ASTM D6348 methods. But by doing so, you eliminate photons of non-interest, which eliminates a lot of what we call shot noise, as well as other types of noises that the detector is able to read extremely low levels of the target compound signal. It's also run at a lower resolution, so we're not using the 0.5 wave number that the MKS instrument typically comes with. And by doing that, you're also eliminating or increasing the signal-to-noise ratio. So this is a real-time or near real-time continuous measurements. These measurements are typically done every 30 seconds or every minute. And I'll show you some information on some of the case studies where we've actually done this for compliance testing. So here's, in fact, what you would see with some of the software that you get with the Starboost technology. So these are essentially what you might say continuous emission monitoring charts, and they're essentially compound concentration versus time. So you can see that it's extremely responsive. You only have a sample volume of 190 milliliters, which allows you to very quickly determine the concentration of the target compounds. And again, this is typically right now used for formaldehyde, which is extremely important because a lot of gas turbine manufacturers or turbine owners are finding that their new turbines are emitting formaldehyde down into the ultra-low formaldehyde range, in other words, the single-digit ppb, whereas the NESHAP, or the max standard for the gas-fired turbines, is set at 91 part per billion. So your standard FTIR can typically get down to about 90 to 100 parts per billion for formaldehyde. This system here can get down to easily 5 to 7 parts per billion of formaldehyde. We can also get down to 20 parts per billion of ethylene oxide, which again is a very hot topic nowadays, and you'll see that also in news reports. In fact, they're shutting down multi-million-dollar facilities because of the politics involved with the ethylene oxide, with community groups and cancer clusters. So it's very important for a facility to understand where they stand and also perform ambient measurements around their facility to determine whether or not their facility is contributing to an increase in the ambient concentrations for that geographic locale. So here you can see that for formaldehyde, these are actual measurements from a case study, test compliance. And typically the detection limit for FTIR technologies generally is, what we use is what's called 3 times the standard deviation of 7 consecutive measurements. Some people would use 8 consecutive measurements. But you can see here in the red box, the standard deviation here of those 8 consecutive measurements is extremely low. And if you multiply that by 3, you easily end up with about 10 parts per billion of formaldehyde. So again, this technology can be developed for other target compounds. In fact, acrolein or acrolein, depending on how you pronounce it, as well as other specific target compounds can also be, the system can be designed to test for them. It's just a matter of using different optical filters and then figuring out the interferences in those regions and adding those to the method. All right, the next technology I want to talk about is called the MAX technology. And the MAX technology actually predates the Starboost technology, although I pioneered and validated it on gas-fired turbines back in 2003. And then it was promptly buried by industry as a development technology. But someone has now productized it and it is now available. Now, the MAX technology is actually a gas chromatograph that's coupled to an FTIR analyzer, and it requires no solvents or extractions, and this is actually compliant with EPA Method 18. So EPA does recognize this as EPA Method 18 because EPA Method 18 essentially states that as long as you're using a gas capillary to separate your compounds, it does not care. It's technology neutral on the actual detectors that you use. So either an FTIR or even a proton transfer time of flight mass spec may be used as your detector, as long as you follow the QA/QC requirements specified in EPA Method 18. Now, in this particular system, it's rather unique in that you're using both a concentration and a separation technique. So what's typically done is that the thermal desorption tubes, otherwise known as TDTs, are either sampled in duplicate, so like Method 18, you have a duplicate measurement, or for engineering and optimization, you can have one tube that's collecting sample and the other tube is actually being analyzed. So the time resolution on these systems is approximately 20 minutes per data point. So you're sampling one, it's then desorbed, and then when that is done, the second sorbent tube is then desorbed for either a paired measurement or a sequential measurement. Now, the way it works is very interesting in that the FTIR sample cell, which is approximately 190 milliliters, is completely evacuated. And then that vacuum actually draws the nitrogen carrier gas through the capillary column. And as those compounds enter the FTIR sample cell, they are then identified and quantified. That particular spectrum is then used as the next background spectrum for the next set of compounds that are exiting the capillary column. And this goes on until no more compounds are exiting the sample capillary column. And by doing this approach, you're eliminating a lot of the interferences that would typically raise the detection limit in a standard FTIR. So here you have both a concentration technique, which improves your detection limit, and then you're eliminating a lot of the interferences by both separating and also using previous compound absorption spectra as the background spectrum for the next set of compounds. A little complicated, but I will be happy to discuss this with anyone offline if there's any interest. Now let's take a look at some of these actual concentration reported numbers from these various techniques. And as I mentioned before, especially with gas-fired turbines, EPA used to have a once in, always in Title V major source, which is 10 tons per year of any single HAP or 25 tons per year of combined HAPs. And it used to be once you were in that category as a major source, there was no way to leave it. But now they're allowing you to reverse that, and by doing so, it can save a company many thousands, if not millions of dollars a year. It also allows them to increase their product line to keep themselves under an air permit limit. And so this is, in fact, a way to increase the bottom line by just adding analytical technology to reduce your detection limit, so that when you add up all those minimum detection limits, it's not putting you over your permit limit. So the AP42 for emission factors for formaldehyde is set at 240 parts per billion, where the CARB 430 method, which was developed a few years ago, essentially had a 180, but a very high standard deviation in that number. It's actually a manual method using liquid impingers. And then if you take a look at the advanced IR, the NACS technology, you can get down to 45 parts per billion, or you can sample longer for lower limits. And then with the optically enhanced FTIR, you can easily get down to the 10 part per billion number. So you can see that's an incredibly significant lowering of the detection limit. So if, in fact, you are not emitting formaldehyde from your process, you can then use this EPA reference method to report much lower detection limits, which helps a facility significantly. So if we take a look at some of the measurements, comparison measurements, so this is actual tests from a natural gas turbine. It's a large mainframe type unit. And here you can see if we use the actual optically enhanced FTIR and the GC coupled FTIR, there's no difference in the reported concentrations of the numbers, at least no significant difference between the two. So you can see that these side-by-side comparisons, one by EPA method 18, the other by EPA method 320, both are in agreement, which is basically important to the regulatory authority as well as to proving that these two technologies work very well. All right, here we're going to talk about a very interesting technology called the proton transfer time of flight mass spectrometer. They really have blown up now in terms of people using them. And what I mean by that is that I can tell you that CARB has purchased 2 units, and the AQMDs in California, 2 of them have just purchased a unit themselves. So I can tell you that there's actually 4 PTR mobile platforms going to be running around California. And Montrose actually has 2 mobile platforms that we keep very busy right now in the Midwest for ethylene oxide, and down in the Houston and Texas area, the Gulf region for BTEX compounds. as well as many other different types of compounds. Everything from smoke analysis to indoor air measurements for sick building syndrome, and even we can measure some of the chemical weapons. In fact, this is one of the only devices that can actually measure TATP, which is the explosive of choice, peroxide base for terrorists nowadays, unfortunately. So how does this work? So essentially what we do here is it looks like a very small dorm room refrigerator. It's about the size of almost 1.5 dorm room refrigerators down in the lower right corner. It essentially is a real-time measurement, so you're getting 1 data point per second in real time. So what happens is you're pulling a small sample of ambient air or compliance or source test air, gas matrix, into the drift chamber, where that drift chamber is then mixed with what we call a reagent gas. And that reagent gas has a proton affinity, and there's many different types of reagent gases you can use. We can actually switch them out every 15 to 20 seconds. And by doing so, we choose a reagent gas that has a proton affinity less than the target compound of interest or target compounds. And by doing that, we're actually transferring a proton from the reagent gas, in other words, a hydrogen atom, to the target compound and increasing its atomic mass by 1. So you have an increase of 1 atomic mass unit. By using the time-of-flight mass spectrometer, we can very accurately measure and differentiate those different atomic mass units. This is very advantageous, but also the beauty of this particular system is that we don't only have to do a proton transfer, we can actually associate a part of the reagent gas to the target compound and then measure an increase in the atomic mass unit. Now we do this with ethylene oxide and acetaldehyde because they are isomers. They have the same molecular mass. So if we were to add a proton to both of those, and they both will pick up a hydrogen atom from the typical reagent gas we use, and you can't tell the difference between them. So in order to separate those two compounds, what we do is we use an association, and we set the controls of the proton transfer unit so that we're actually cleaving a fragment of the reagent gas with an atomic mass of, I believe it's 34, and we're attaching that to the atomic mass of the ethylene oxide, which the acetaldehyde will not pick up that fragment, and therefore we can differentiate between the two compounds. And we've done this very successfully at many different places throughout the Midwest. So this is typically what the mobile platform looks like. It's a very nondescript white band that we can use to actually do real-time mapping around a facility or in a community. We also take this out for odor complaints. It's very good at seeing many types of the odorous compounds, which are primarily sulfur compounds and some of the nitrogen compounds, the amines, that typically you'll have a lot of communities complaining about. So we can very quickly deploy and determine not only what the compounds are and the concentrations of those compounds, but also the platform comes equipped with a GPS and a meteorological station, which allows us to use our Montrose triangulation platform and very quickly determine where those compounds are coming from. So it is up to an industry's best interest to have their own defensible data so that if they're accused of various either releases of odorous compounds or carcinogens, that they can very quickly point to this data. And it is an absolute measurement in time and space, which means that it's extremely accurate, it's extremely reproducible, and it comes with either a snorkel, so we can ride around and measure ambient air, or it comes with a 200-foot heated line, which we roll out of the back, and then we can either put into a source matrix and dilute and then do the measurements, or we can actually enter into a facility and sniff around to find extremely long, small leaks of very toxic compounds. All right, so the advantages of that, right now we are undergoing an alternative test method to be able to use the PTR time of flight in real time as an approved EPA method. But in cases where we have to produce compliance data, we couple a GC to the front end of this, and then it becomes EPA method 18, and we use the PTR as the detection device. So now we're going from a 1 data point per second to approximately 1 data point every 12 to 15 minutes, depending on the compounds of interest. And then hence it becomes EPA compliance grade data. And EPA has agreed that this can be used as a detection device for EPA method 18. All right, so here's some case studies of some of these studies, and here we actually did a loading dock where we pulled the van into a loading dock area where they're loading 18-wheelers for petroleum products, both gasoline and diesel, and then they're also bringing in tanker loads of ethanol where they're loading into tanks, and then they're mixing the ethanol with the gasoline as per allowed to create the ethanol blended fuels that we see used in the wintertime. And here you can actually see that every time a tanker truck pulls into the facility, you have a signature of the ethanol that's being released just in fugitives from that unloading of ethanol. Now, this might be from the connection, it might be from a spill pulling the line off, but it's interesting to see here that throughout the day, it seems that either the temperature is going up and you're getting more fugitives, or the guys unloading the ethanol are getting a little sloppier. It's hard to determine those things, but at the same time, you can see the detection levels here are extremely low. In the next study, we actually plotted many different communities and around facilities in the Midwest area where a lot of ethylene oxide is either produced or used for sterilization. And in this particular case, it's very easy that you can just drive the vehicle around and you can map upwind and downwind of a facility, or keep making circles around the facility for days or weeks at a time to determine whether or not the facility has issues. And what we're finding is that in urban areas, you can actually see very elevated levels of ethylene oxide. That is, in fact, around airports, industrial areas, old diesel engines can produce it, lawnmowers and leaf burning and many other different everyday activities produce ethylene oxide. So again, it's very important for an industry to be able to defend itself and say that, the urban ambient levels of ethylene oxide upwind of their facility is actually higher than or the same as downwind of their facility. Therefore, they are not causing an issue. And so there's a lot of attorneys involved in this, but you can see that we can provide some very interesting data. So the next slide, I'll show you a little video clip. And can you see the video clip right now being played? Because I cannot. Okay, I'm being told that it is playing. And essentially, now this becomes very powerful data. You have a lot of data. You have a lot of sensitive data, extremely low concentrations, and you can make any kind of presentation you want based upon the data. And there you can see that you can do some fancy things with the data, and this is both production quality as well as the defensible data. But this, either using an alternative test method or going and doing side-by-side method 18, in other words, using the GC to prove these numbers and then switching back to real time and back and forth, we can provide both compliance data and optics and then engineering data to boot. Now, we always keep in our eyes on, oops. Okay, I think I need to, there we go. All right. Montrose also is always keeping its eye out for some of the latest, greatest technologies, and that includes sensors and various things. Here, we're working very closely with a company that is now generating a laser-based FTIR. In other words, a lot of those large footprint technologies are being used all over California for open path measurements along fence lines. That includes open path FTIR as well as UV-DOAS and TDLs. We actually have a validation software called EPAC that can reduce the detection limits for those technologies to what we've seen using real data is up to 3 times better detection limits, and eliminating false positives and false negatives by 90%. And I don't have any slides to present that, but if anyone's interested, please contact me. I'd be happy to discuss. And we're in negotiations to use this as third-party validation for a lot of the existing. But this particular FTIR laser-based system is extremely advanced in that now you can put one of these basically in the center of the facility on a tower or a pole, and then use these very small single retro cubes all around the facility or the fence line or even farther. They're very small, and the laser will actually find each one of these and lock onto the hotspot, which essentially means that you don't have alignment drifts that you do with the typical 32 or 64 array retros that are used now. And it's a very quickly can step through the retros, and now you can topographically map an entire facility. Now, there is a push to eliminate leak detection and repair programs, which are very labor intensive, with some of these types of technologies that can actually then determine whether you have leaks, find where those leaks are, as opposed to having a bunch of guys and girls running around the facility with sniffers trying to figure out where the leaks are coming from. All right, the next particular technology that Montrose has invested in is what's called a QCL photoacoustic system. So it's essentially a very sensitive microphone placed in a sample cell. So what happens is you hit the sample matrix, and for this particular case we use ambient. What we're trying to do here is to create intelligent, actionable data with the 325B passive sorbent tubes that every refinery in the U.S. is required to deploy. And so if people are having a problem with these sorbent tubes, they put them out every 2 weeks. They get sent to the laboratory. And then if they have elevated levels of benzene above ambient levels for that geographic locale, then essentially they're required to do something about it. All right, that might mean putting in a site-specific test plan, trying to figure out where the emissions are coming from. And with this particular device, we're trying to obtain low levels of benzene with high temporal resolution. In other words, very quickly updating the data. And by doing so, when you couple that to a meteorological station, you can very quickly determine where the benzene is coming from. All right, so what we're doing here is using a micro electromechanical microphone within the sample cell. We're hitting the benzene molecule with a QCL laser at a frequency that it will absorb, and what happens is that molecule heats up, creates a pressure pulse, and that pressure pulse can actually be measured over 4 orders of magnitude. The measurements that we've tested on the Gen 1, and they're undergoing testing right now in Denver at our facility, is less than 10 ppb in 5 minutes, or less than 30 ppb in 30 seconds. But in fact, there is a new QCL out there that we're getting ready to test, and this particular laser-based device can measure the benzene region much more with much better signal, which allows us to get down to 1 part per billion in 30 seconds. So we'll be marketing these shortly. Now let's talk about sensor platforms and capabilities. So as I mentioned before, with the EPA benzene tubes, the 325Bs, you're required to put passive tubes out around your facility of various intervals to protect receptors down site. And that might be a park, a school, a community area, even residential areas. And so if you get those results back and you have higher levels, then you really are required to look at it. And that data also follows you for the next year because it's a yearly rolling average. So anytime a facility can figure out where the emissions are coming from, whether they're off-site or on-site is very advantageous. So now again, we can also put out low-cost sensors for total VOCs or particulate and many other different types of compounds. And with the high temporal resolution coupled to our platforms, we can very quickly figure out what's going on. Now, another advantage of this is that EPA allows you, if benzene is moving onto your facility, and this happens a lot in the Houston area, where you have a refinery next to a wastewater treatment plant, next to a incinerator, it becomes very confusing. So this type of system, when you have high temporal resolution and the platform, if the benzene or other types of compounds are moving onto your facility, you can actually start to sum the mass or the flux moving onto your facility, and you're allowed to subtract that out of your tubes. It also tells you where it's coming from, so you might be able to alert your neighbor that they're creating a problem on your facility. So how does this work? Okay, well, we use these sensors, and they can be anything from, like I said, GC-based, which is a little lower temporal resolution, about every 15 minutes, sometimes a half hour. There are some newer FTIRs out there that can do it in approximately 8 to 10 minutes, from what I understand. We've been in discussions of some of those. But essentially, if you have a high temporal resolution monitor, what you can do is quickly determine this. And here's a case study where we actually put out a bunch of sensors around a facility that was having issues. And here you can see the sensors, the 4 sensors here are located along that ship channel up in the upper corner of the upper fence line of this green area. And now this was originally a movie, but to save time, I pulled some excerpts from it. So in this particular case, you can see there's a little red dot here where one of the sensors has actually picked up a plume. And as that sensor continues to pick up plume readings every time it measures, which can be as small as every 1 second, sometimes 5 seconds, what it starts to do is generate a point flux measurement. And that means that essentially the concentration of the plume that's reaching that sensor can actually then be used to determine the distance. Because like a dispersion model, when you release an amount of gas, it starts to spread out downwind according to Gaussian or Lorentzian laws. And by doing so, that actually gives us a little bit of information about the distance where that particular compound came from and how strong the plume was. So even with one sensor, we can generally locate an area of where it's coming from. But as soon, and the more data that rolls in, you can actually see that the location where the plume, the source of emissions is coming from, actually starts to zero in on that particular location. But as soon as that plume gets big enough where 2 sensors or more pick up the plume, well, now we can use triangulation, and we use a very sophisticated geometric model to do this with some Gaussian dispersion, but it can very quickly triangulate right back to the source of the location. And in this particular case, this was in fact a benzene tank that was causing an issue. Now, I'm going to switch again now into drones. And so drone sensors are becoming much more popular. Problem is sensors are hot and cold. Differences between low-cost sensors varies greatly. Some do much better than others, and of course different classes of sensors do better than others. Right now, methane, I've just seen the first methane low-cost sensor actually come out that's really worth its salt. And now there still needs to be some more work on metal oxide type VOC sensors, but we do keep our eyes on those. And of course, you always have PIDs, which are not very specific, but at the same time can provide important and intelligent, actionable data. In this particular case, we've used very good sensors to measure NOx emissions and CO2, and EPA is in fact involved in this particular study. We're going for an alternative test method to be able to use drones with sensors, flying them over natural gas-fired boiler plumes, and being able to measure the emissions in compliance level. So this is important. In fact, if you look down here at this lower table and on the bottom here, you can see the difference between the CEM reference method data. We've come in and done a side-by-side relative accuracy test audit to check that CEM data. And then we've used the drone with this particular sensor that EPA is involved with to fly over the plumes. And then we use method 19 to determine the carbon ratios based on the fuel carbon ratios, which we can then determine the velocity in the stack. And with the velocity, we can then determine the volumetric flow rate and then calculate the concentration. So here you can see that there's really no statistically significant difference between this data, and this is very promising, and this is our proof of concept, and now we'll be undergoing a very in-depth study, of course, using redundant systems and EPA method 301 to prove out that this is in fact a viable alternative. And this all started because a Fortune 100 company had a few safety issues with elevated work. There were a few deaths, and it came down from the CEO that we don't want to do any more elevated work if there's an alternative technique to do it. So this is really what drove this particular development. So low-cost sensors, to wrap my section up, is essentially, now again, there's various differences. We are involved with the city of Denver. We put out particulate low-cost sensors throughout the city of Denver. And what they're doing there is they're trying to determine what the cost basis is in lost GDP for kids that have asthma and have to visit the nurse in the school because of an asthma attack, and try to correlate that with PM 2.5 data. So if there's correlation between PM 2.5 and asthma cases, you can now actually put a cost on that lost GDP. In other words, the students' parents have to leave work, they have to come in and get their child, they have to take them to get medical assistance. All of that has a price on it. And so what is the difference between the cost of high PM 2.5 versus the cost of lost GDP? So this is where this type of data is going, and citizen scientists are getting very organized now, and you're seeing a lot more of these types of sensors. But in a nutshell, these sensors right now, they are not reference grade yet, right? Eventually some might get there, but by having networks of these sensors, it does provide useful data to indicate problems or issues. And then what we do is we come in with the federal equivalency methods, the reference methods to confirm the sensor data itself. And we have some very good platforms and data management systems to do this. So with that, I'm going to now turn over my mic over to Daniel Fitzgerald, who's going to talk about OTN37. Thank you for your time.
Thank you, Pete. I appreciate that. Good presentation. My presentation is talking about a new methodology that's out there and looking for particulate matter, specifically looking at PM 2.5 It is also set at PM10 as well, but with the regulations that are out there, PM2.5 is becoming a more prevalent measurement that is needed by the industries. In this case, what we're finding out is PM2.5 from combustion sources, essentially gaseous combustion sources, has a high bias due to the combustion products. And in some cases, if there is some potential sulfate or even a cation such as ammonia from SCR, such as or from an SCR, and you actually have those combined, you can find an artifact in the conventional method 202, which is being used prevalent today by EPA for looking at condensable particulate. And of course, when we say condensable, we're looking at primary particulate matter. Secondary would be something that is much further downwind from a source that may be photochemically reactive. What we're actually looking at is what would be the condensable particulate as the particulate exits the stack and becomes closer to ambient temperature conditions. So the 202 that is out there right now actually condenses the stack gas upon passing through a filter. And as it condenses, it runs through a condensate coil where it actually, the stack gas is cooling down but does make contact with water. And on making contact with water, that water vapor facilitates the combination of cations and anions together in forming artifacts in the impingers that highly bias the particulate or condensable particulate matter emissions and are actually considered part of the PM2.5 measurement. What OTN37 is doing is actually looking at a simulation of the dropout of PM or condensable PM as it leaves the stack. And that is being done by actually combining dilution air with the sample gas, not in the presence of water vapor or water moisture that is at condensing at a condensation situation and causing this artifact. This method actually started out as Conditional Test Method 37 and was actually upgraded to Other Test Method 37. That was done back in May of 2018. The actual thought here is now that it's another test method, that it is more readily accepted, but it is still a method that must take regulatory agency approval before it can be employed. Our next slide here actually gives you an idea of what we're looking at coming out of the actual stack and how the condensables and the gases combine as compared to the lower section is actually depicting the sampling system and assimilating the actual dropout of a plume in the atmosphere. Real quickly, we have a OTN37 diagram here. That this diagram actually shows the mixing chamber, the resonance time. The added advantage to looking at the OTN37 is that we've actually taken and combined the filterable particulate and the condensable particulate into one filter, whereas the method 202 actually separates it into a front half and back half. By having one filter that looks at the total PM2.5, or it could be a PM10 if you did not require a PM2.5 cyclone separator. And all that is actually in one measurement on one filter, therefore reducing the sense of error. The next picture, our next slide, will actually show you a cassette of what is used for the OTN37. This is a Teflon membrane filter. The advantage of this over a typical method 201A, which uses a glass fiber filter, is the fact that the Teflon membrane filter does not flake or actually be subject to tearing. It's actually encased in a cassette here where the actual user does not actually handle the filter. It's pre-teared prior and then sent back to the lab where it's weighed to the nearest 1 microgram. Typical method 201A, we're looking at about a half of a milligram as our detection limit, where here we're getting into micrograms of actual particulate gain. What I'm looking at here is a conditional test method. It actually is showing some CTM039 results that were actually collected prior to turning it over to OTN37, but the methodology was the same. We're actually showing a history of what the old method 202 looked like in as far as collecting emissions as compared to the CTM039 at that point. And as you can see, in some cases, this is as much as, in most cases, 25% less. I will say in some cases when we do see SCR, we do see that there is still an amount of condensable particulate that we're finding that actually forms right before it, or just as it condenses out of the stack. Real quick, our next slide is showing a CTM or an OTN37 setup on a stack. As you can see, it's a lot more precarious than a method 5 or a method 201A system that is normally set up, along with the method 202 impingers. Next slide is just another quick one, and I apologize that I'm going through quickly here. I just realized that we're up against time. The next slide is showing some of the typical test results that we've had as compared to AP42. And it's one of the things that I wanted to highlight about the method is that in some cases where somebody or a facility wants to increase the plant, in other words, they want to go ahead and put in new sources, but yet they don't want to kick in PSD, they can actually go back and look at their sources where they assumed AP42 factors and petition to go ahead and do actual testing on their sources to demonstrate what the actual emissions are. That way that opens up leeway and therefore maybe not kicking in PSD based upon actually measuring the particulate emissions from the stacks. At this point in time, like I said, I hurried through this. I wanted to leave a time for questions from our audience. And so if there are any questions, we're here to answer those.
Great. The first question is, on the mobile platform, is it affected by the van's exhaust when running?
It can, yes, but generally it depends on the compounds we're looking for. This van is a diesel van, and a lot of times what we'll do is when we find a plume, we will actually stop, turn the engine off, right, do the measurements, run the GPS and platform in order to get a fix of where it's coming from before we move to the next spot. So depending on the compounds, it could. So we have to be very careful of that.
Okay. The next question is, are the fence line measurements in the California refineries accurate, and can they be used for violations or risk assessments?
California, it's a good question. California has made industry spend millions and millions and millions of dollars on these fence line line monitoring systems. However, these fence line monitoring systems is what's called a 1D OTN10 procedure, which means that they basically are using one retroreflector at a distance of up to 500 meters. By doing that, these become just alarm systems, because in order to determine whether the plume has been completely captured or whether it's homogeneous throughout the entire pathway, you need either multiple retroreflectors to do that, or you need some other technique to walk or have some point sensors to prove out that you're capturing the entire plume. If you are not, and these systems cannot do that because they are 1D systems, only one retro, there's no way that they can do that. If that was in a court of law, I could drive an 18-wheeler through those numbers. They would not stand up in a court of law. They are an alarm system and an indicator of a problem. So they could have required more retros and gotten some much more accurate data, which could then have been used for possibly NOVs or risk assessments. But for the most part, they are alarm systems, and then we can always go in if there's a problem and get the real numbers by either walking the entire path length with something like a PTR or point sensors or some other way to do that, to determine whether or not you're within an order of magnitude of the actual number. It also doesn't tell you whether the plume is going over the path length. So there are a lot of problems, and I think when these systems start up, there's going to be a ton of issues with the softwares that are used. I've been doing open path measurements for 30 years on volcanoes around the world, as well as the first consent decree in California back 20 years ago, the first open path system. And I can tell you that there were better ways to do this, but at the same time, the data is going to be all over the place, and they really need third-party validation on that data.
Okay, another question. Have you turbined PM emissions with a lower detection limit method?
Yes, we actually do have emission data on turbines. We have conducted that work. We'd be more than happy to talk to any person that would like to discuss that, but I don't have the data in front of me, but it's relatively about 25% lower than some of the data that by the conventional 201A and 202.
Okay, and last question. Can you use a drone to test for other pollutants besides CO or CO2?
Sure. Whatever, if it's a compound-specific sensor, we can certainly use that. The issue with the drones is what's the detection limit, right? If you're looking for, NOx or SO2, where you have ppm levels of compounds, it's generally easy, right? Because you can measure well. When you're talking about, 1 ppm or less, then that's going to be problematic unless the drone has a probe and you're actually sampling right at the tip of the stack, or even within a port. You can actually do that nowadays. Then you can do that, sure. It depends on the type of sensor and, of course, the power needs of the sensor and the weight of the sensor.
Great. Thank you. And that's all the time that we have for the Q&A session. Thanks again, Montrose Environmental, for a great presentation. Please visit them at montrose-env.com. The on-demand version of this presentation will be available in about 2 hours at bicwebinars.com. Feel free to watch it again and share with your colleagues. On behalf of BIC, thank you.